We're going to continue our discussion of spectroscopy and light by looking at this Bohr model of the atom. Niels Bohr was a scientist who was one of the first people to really say that electrons have specific paths that they orbit around the nucleus. And his model is used a lot to help us understand what's going on with electrons. Interestingly, it's not quite right. There's actually a lot of inaccuracies with the Bohr model, but for our purposes in ESS and even chemistry classes, it's good enough to help us understand what we need to understand. So let's go to our notes here. Yours should say slide 10. And this is a Bohr, B-O-H-R model of an atom. Now I want you to see, I'm going to put my atom at the ground state here, and it's at the ground state because it's at the lowest position that it can be, right? So back to your notes, energy is absorbed when an electron jumps from orbit 1 to orbit 2. Or really, if the atom absorbs energy, we might get a jump of the electron. So watch what happens when I put a little photon of light in here. And notice the color of light was kind of an orangish color, okay, to get from the first energy level to the second energy level. Now, back to your notes. Energy is released when the electron jumps from orbit 2 to orbit 1. Now watch what happens in the emission spectrum here when I cause this electron to go back down to the ground state. It's going to give off a wavelength of orange. This is the absorption spectrum, right? We just looked at those in our notes, and this is what the emission spectrum would look like. Now I did that really slow. I made it jump up to an excited state, and then I talked a little bit and had it jump back down. In reality, this would happen very quickly. Almost instantly after the electron jumped to an excited state, it would jump back down to a ground state. Now let's look at a bigger jump. Let's say I had a higher energy photon than orange, something higher come in, and it caused the electron to jump 2 energy levels. So let's make it jump to the 3rd energy level. Notice what that took. It took a higher energy photon. Blue is higher energy than red and orange. So if we look at this part of the electromagnetic spectrum, infrared is lower energy, red and that part of the visible spectrum is a little higher, violet and blue are higher energy, and then ultraviolet is even higher, and that's when we get into rays that can actually harm us. Ultraviolet, that's what gives us a sunburn and can give us skin cancer. That's why we use sunscreen. So this is only a part of the spectrum, but it shows you a lot of the different wavelengths that can be absorbed or emitted by atoms. So now back to our atom here. That electron is in an excited state, and if I want it to jump back down, think about what wavelength of light is going to be given off here if I go from the 3rd to the 1st energy level. If you guessed blue, you're right. So again, the black lines in the absorption spectrum would be the same as the colored lines in the emission spectrum. Okay. Now what if I even put a higher energy photon in? Now think, what would be higher energy than blue or purple light? If you're thinking ultraviolet, you're right. So let's see what it takes to get it to the 4th energy level. That took a higher energy UV ray. And when that electron falls back down, it's going to give off that same wavelength. Now, we wouldn't be able to see this because it's in the ultraviolet, and our eyes are only able to detect wavelengths in the visible range, which is actually a really tiny part of the electromagnetic spectrum. But we wouldn't be able to see UV without some special instruments. Now I keep jumping around, so if we go back to your notes, let's fill that in, and maybe you've already done that. If the orbits were moved closer together, what would happen? So let's try that. Let's move these orbits together. All right, I'm going to move this orbit closer to this one and this one closer to this one, so they're all a little tighter together. So remember, to get from the 1st to the 2nd, it took a yellow or orange wavelength. To get to from the 1st to the 3rd, it was blue, and 1st to the 4th, let's make this one a little smaller too, was ultraviolet. Let's reset this. Now what do you think it's going to take here to go from first to second? This is actually a way lower energy wave, infrared, and it's not even on our chart here. We'd have to expand it out to see it. And then if, of course, when it jumps back down, it would give off that same wavelength. But again, we wouldn't be able to see that when it's infrared. Okay, what about to the third? Let's make it jump to the third. And now we're on our chart. We're still in the infrared, which is pretty low energy. But why did it take less energy in this atom to go from the first to the third than it did in the previous atom before we moved the energy levels around? Well, the energy levels are spaced differently now. Okay, so if that jumps back to the first energy level, that's what we get. Now let's go to the fourth. What do you predict? What color? Green on this one. Okay, so it took green energy, which was higher here. But remember, in our last one, to go from the first to the fourth energy level, it took a wavelength of higher energy UV light because they were spaced farther apart. Guys, this gets into why do elements all have different emission spectrum whenever we look at them. When we do our mysteries of light activity and we look at different elements, every element has a unique fingerprint. Well, why is that? That's because the spacing, or where those electrons are for each atom, is a little bit different. So in one atom, let's just say hydrogen, the spacing might look like this, and so you get different absorption and emission spectrum for hydrogen. But in helium, the spacing might be a little different. And so when that atom jumps around, it absorbs and emits different wavelengths of light, giving our spectrum for helium, would look different than the one for hydrogen. So that different spacing, also the number of electrons an atom can have or has, definitely affects its spectrum as well. So these are all key things when we talk about spectroscopy and the Bohr model of the atom. Now that we've played around, we've talked about spectroscopy, we've seen it in action here a little bit and how this all works. Now you should go and answer the spectroscopy practice problems that are also in your notes, and those will help you get a better understanding and make sure you can apply this knowledge to some real-world situations and understand what we're doing here. So take some time to complete that. You may, because it talks about different energies and frequencies and whatnot of light, you may need to do a little bit of outside research on the electromagnetic spectrum, specifically what colors have larger and shorter wavelengths or more or less energy, because that's going to be really important that you can connect color to energy and wavelength. Those are all important factors in all of this.